understand buffers. And buffers are nothing more than the common ion effect. And we've already covered this back in equilibrium. Okay, so it's not new to you guys. It's just that it's in the context of acid-base chemistry. So let me go ahead and start this. Okay, common ion effect. Let me just give you a reminder. Whenever you have a common ion in solution, remember, it causes that equilibrium to go in the reverse order. So the forward direction is see some headwinds. It doesn't, it's not as progressive. It's not as efficient when you have a common ion. And we saw that when we had the acetate ion, acetic acid example. Here we have, let's take a look at just plain acetic acid. Plain acetic acid is this right here. We abbreviated HAC. This right here is the acetate ion, and this is your hydrogen. And remember that we can do that because the chemistry is the hydrogen coming off the acetate ion. The acetate ion is not going to do anything else, so we can just abbreviate it AC, acetate. Now, the question is, I have a 0.10 molar of this. My Ka for this is 1.8 times 10 to the minus 5. What's the amount of hydronium that is produced? And therefore, what is the pH? This is a classic example of doing the shortcut. The shortcut is going to be 0.1 molar. That's the initial concentration of the acetic acid. And the Ka is 1.8 times 10 to the minus 5. You multiply that out, you take the square root of that, you get the hydronium ion concentration. Okay, and that's exactly what you see right here. Okay, that comes out to 1.34 times 10 to the minus 3. And if you take the negative log of that, that's 2.87. This is a solution is acidic. It's got a pH below 7. Now, look what happens when we have a common ion. When we have a common ion, let me clear this. Let's say that we mix into our beaker not only acetic acid, but sodium acetate. So in here, we've got acetic acid in water, but we also have the acetate ion. Okay, that's a common ion introduced from the sodium acetate. So this is our ice table. Our ice table is acetic acid. It just tells us right here we got a 0.1 molar acetic acid and we have a 0.1 molar sodium acetate. That means that the acetate ion in sodium acetate is also 0.1 molar. Okay, so we have our reaction. Acetic acid right here, water, acetate ion right here, and it's also going to form hydronium. Why? Because acetic acid is a weak acid. It's going to donate its hydrogen to water, forming hydronium, and you get the acetate ion. The initial line is 0.1 here and 0.1 here. If we do our mass action expression, Ka is equal to hydronium times the acetate ion times the acetic acid. But we can make simplifying assumption and say that X is going to be very small. Why? Because Ka is in the order of 10 to the minus 5. The X that's given off here is going to be very small. Why? Because not much of the hydrogen comes off that acetate because, again, the equilibrium constant is 1.8 times 10 minus 5. Guess what? These two are equal. 0.1 minus X, 0.1 plus X. X is negligible. These two cancels out. The Ka is equal to the hydronium ion concentration. And that comes out to the Ka is 1.8 times 10 to the minus 5. That's your hydronium ion concentration. Compare that to up here where it was 1.34 times 10 minus 3. This is much smaller. In other words, the reaction doesn't produce much more hydronium. 1.8 times 10 minus 5 is a smaller number than 1.3 times 10 minus 3. Also, the pH is 4.74. And if you calculate the percent dissociation, remember the percent dissociation is how much of that is changed versus the initial concentration. So this would be the hydronium ion concentration. That's the amount that was given, that was provided. That's 1.8 divided by zero point 0.1. That's a 0.0180% ionization. If you compare that to the top is 1.34% ionization. So in other words, in the presence of a common ion, the efficiency of that reaction to produce hydronium is deterred. It's basically lowered, and that's true. And that's why we can use this concept for buffers, because buffers are solutions in which the hydronium ion concentration doesn't go very high or doesn't change significantly, or the hydroxide ion concentration doesn't change significantly. When you have a chemical in solution so that the hydronium or the hydroxide doesn't change significantly, so the pH remains basically constant, the pH doesn't change, then you have a buffer solution. And that's why you use buffered assays in biology, because any contamination that you do to your assays is not going to ruin the experiment, because the solution will stay at that particular narrow pH range. Okay, so for those of you who are going on to biochemistry or biology and you're doing all kinds of experiment with biological system, you got to know buffers. You got to know buffers. Important. The important thing about buffers is that there's a shorthand equation you can use. Okay, so it makes it super easy to calculate the pH of the solution when you have a buffer system. Okay, so let's consider our previous example. Okay, this is the acetate ion. This is acetic acid. This is the acetate ion. Change my color here. And when you write the Ka for this, the mass action expression, you get this hydronium, that's this right here, times the conjugate over the acid. That's just the mass action expression of the acetic acid. The key here is that in acid-base chemistry, you're usually the typical question is generally, is the solution acidic or basic? If it's acidic or basic, calculate the hydronium ion concentration or the hydroxide ion concentration, and what is the pH of the solution? That's the type of question that you see in acid-base chemistry. Acidic or basic, calculate the pH. So, isn't this the chemical right here responsible for the pH of the solution? So if we solve this for hydronium, okay, that means that we're going to throw everything to the other side. What we get is hydronium is equal to Ka times HAC, that's the acid, over AC minus, that's the base. Okay, I'm just rearranging that equation. Now, remember what the P function is? The P is the negative log of the hydronium ion concentration. That's the P function. The P function is the negative log. So when I apply a P function for both of these, and when I do that, then I would get this. This part right here is just the pH. So the pH is equal to, we're going to do a distribution, the negative log of the Ka minus the negative log of the acid over the base. Okay, I can do that because what we're doing is this is a negative log function. Okay, that's a negative log. The key here is this amazing equation, and it has a special name. The negative log of the Ka is just the pKa. Okay, it's just a pKa. And then we're going to flip these two. You can do this in math to make that positive. And I'm just going to call this the conjugate base over the conjugate acid. That equation you've seen before. Uh, if you've taken biology, it's called the Henderson-Hasselbalch equation. Whenever you have a buffer system, you can use this equation and you could fully deploy it and calculate the pH of the solution. Okay, let me erase this so you can see its derivation. That's the derivation. It comes from the ice table, but this right here is what we end up with. Okay, notice this is a plus, not a negative. And that's because we switch these two terms so that the base is on top and the acid's on the bottom. Conjugate base over the conjugate acid. And they have to be present in order for you to have a buffer. If one of them is absent, you don't have a buffer. They both have to be present at equilibrium. Then you have a buffer. Okay? If one of them is absent, you don't have a buffer because you can't plug into this equation. Anyway, here's the result. Why is this important? Because it makes the titration curve calculation super easy, as long as you recognize the fact that you have a buffer situation. Okay, so here's an example. Okay, again, this is just the application of the Henderson-Hasselbalch equation. You can use this equation to calculate pH. You can use the converse of that and calculate the pOH if you have a pKb. Notice it's a pKb plus the log, and now the acid's on top and the conjugate base is on the bottom. It's just the inverse of that. So these are two equations that you should write down somewhere, because when you have a buffer, you don't have to go through the ice table. You can just go straight here, but recognize that you have a buffer. Otherwise, all bets are off. The pKa is not 1.8 times 10 to the minus 5. The negative log, there's a question of 1.8 times 10 to the minus 5, I believe is, let me just see. I believe it's 4.74. Okay, that is right here, 4.74. So that the pKa here is 4.74. And then you have to calculate this based on the concentrations of the acids and base. In our original problem, when these two are equal, see how this is 0.1 and this is 0.1? Well, these are not zero. It's basically log of 0.1 over 0.1. The log of 1 is 0. Okay? Not that the concentration of the conjugate acid and the conjugate base are 0. It's that they both are equal. So it's log of 1. And when you take the log of 1, that is equal to 0. So here, if we remember our shortcut and use the Henderson-Hasselbalch equation right away in our previous problem, the pH is equal to the pKa, which was 4.74. And you saw that right here. Oops, sorry. Saw that right here in this problem. Let me clear this. So instead of doing all this math, I could have just gone right here and do that. It's a shortcut that you guys need to use, but use it in the context of the chemistry that is occurring. It's always about the chemistry. If you don't understand the chemistry, if you don't understand how these little atoms manipulate themselves around, then you're going to get lost in which math equations to use. But if you recognize what's going on, draw yourself a little picture, then you know exactly what equations to use in these types of problems. Okay, so let me go ahead and finish this up right here, and then I will give you a head start of what we're going to be talking about next time. Okay, here's the example that I was just talking about. These two are equal. Whenever the acid and the base have equal concentration, pH is equal to the pKa. These two are equal. pH, I don't even have to lift a pencil. These two are equal. They cancel out in the log term. pH equals to pKa. Okay, that's what happens. Now, why are buffer systems so important? Here's another example. Okay, I'll do this real quickly. here we have acetic acid, and now acetate ions 0.1, acetic acid's 0.2. So pH equals 4.74 plus log. The acid is 0.2, the base is 0.1. If I do that, I could calculate the pH of this solution. Okay, what is the pH of this buffer solution? It's whatever this number comes out to be. 0.1 over 0.2, that's 1 over 2. The log of 2, or zero point 0.5, is going to be log base 10. Always remember it's log base 10. This is minus 3.301, and you add that to 4.74, and you get a pH of 4.44. That's the pH of that solution. Okay. Calculate the pH when 1 ml of hydrochloric acid is added to 100 mils. When you have 1 ml of hydrochloric acid in 100 milliliters, that's basically a dilution. Okay. Remember, the new volume is 101 milliliters. The moles of 1 milliliters, 1 0.1 molar. So if you got 0.1 molar times 1 milliliters, that's 0.1 millimole. 0.1 millimole divided by 101 milliliters, that's our new concentration. When you add 100 milliliters of water to 1 ml of hydrochloric acid, that is 9.9 times 10 to the minus 4 molar. Okay, so the pH, that's our hydrogen ion concentration. So the pH of that is just going to be the negative log of that number. That's 3. So the question is, let me show you a picture of what's going on. Okay, you have a beaker of water. In here you've got acetic acid and acetate ion, and you're going to basically you have this as a buffer system, and that solution has a buffer of 4. What was the 443? That's the pH. Okay, in this particular case, so we have an acetic acid, we contaminated, the pH on this particular thing is 4.43. The pH of that solution is not going to change very much. Here we have 100 milliliters of water, and we add to it 1 milliliter of hydrochloric acid, and that's 0.100 molar. And initially this water has a pH of 7. But when you contaminate it with 1 ml of water, the pH now drops to about 3.0. So the difference, just based on 1 milliliters of hydrochloric acid being adding to that water, is a difference of 4. That's a dramatic change if you're working with systems in which it's pH sensitive. The buffer system will absorb that excess hydrochloric acid, and the solution should stay within 4.43. That's the magic of buffer solutions. Okay, so that's what we see right here. And the second part, I do the math for you, and you can see that the second part right here, this, if you contaminate the buffer solution with hydrochloric acid, it goes from 4.44 to 4.43, a difference of minus 0.01. On the other hand, for the acid, if you have 100 milliliters of water and you contaminate it with 1 ml of hydrochloric acid, the pH changed by 4. So the main take-home message here is that you want buffer solution if you want resistance of pH change. Can you describe the SRFC? What does that mean? I have to describe it next time because we won't have time today, but SRFC basically is stoichiometric. First part of the reaction is stoichiometric, and whenever we do stoichiometry, we deal with moles, okay? And then when you have equilibrium, you don't deal with moles, you deal with molarity. So whenever you have stoichiometry problem, and this is a stoichiometry problem in that you're going to see that the hydrochloric acid is going to donate all its hydrogen to water and form you, so you form stoichiometric amount of hydronium ion. The amount of hydronium ion that you form over the volume total is the concentration of the hydronium ion, and you can get the pH from that, okay? Um, so again, the essential feature of buffer solutions is that when you contaminate buffer solutions, these chemicals will either absorb or produce chemicals so that the hydronium or the hydroxide concentration doesn't change. Let me just spend 5 minutes and explain that in the context of your blood, okay? Your blood is buffered, and it has a buffer of about 7.35 to 7.45. Anything below that, you get acidosis, you get prolonged acidosis, you'll be dead. Anything above that, you get alkalosis, prolonged alkalosis, you'll be dead as well. So the way we govern the pH of our blood so that it's within this narrow region is that we have chemicals, proteins, phosphate, but more importantly, we have carbonate ions. And carbonates are great buffer systems. And the reason why they're great buffer systems is because you've got two chemicals here, bicarbonate and carbonic acid, in which it will react with hydronium or hydroxide to remove that. And the reason why we need to remove hydronium or hydroxide, okay, is because your pH is directly influenced by the concentration of hydronium. Remember, pH is equal to the negative log of the hydronium ion concentration. pH is not equal to the bicarbonate concentration. It's not equal to the carbonic acid concentration. It's equal to the hydronium ion concentration. So you gotta have a chemical that removes the hydronium or the hydroxide, they're related by the water, in order for that pH not to change. And that's what buffers do, okay? Acidosis, whenever your pH drops below 7.35, it's because there's too much hydronium ion in your blood, or more acid in your blood, or you're removing the hydroxide. And you get that by respiratory acidosis. If you hypoventilate means that you can't breathe, then the carbonic acid cannot break down to carbon dioxide and water, okay? That channel, when we store up too much carbonic acid, we breathe it out. If that channel is cut off, then this guy will form back the bicarbonate and hydrogen ions. And so we get an increase in our hydronium ion concentration, a decrease of our blood pH. We have acidosis. We also can get acidosis by metabolic, either by starving or fasting or heavy exercise. We produce a lot of lactic acid, or we burn a lot of fatty acids. So these are the mechanisms. You guys could read this, okay? For alkalosis, we have pH greater than 7.45. And again, these are the symptoms. You will die if you have alkalosis. We can get respiratory alkalosis. Again, this is when we breathe too much. This channel breaks down carbonic acid to carbon dioxide and water. And so we can't, what happens is that the equilibrium now is going to do this. Any acid in our body will feed into carbonic acid because we're constantly breathing and we're breaking down the carbonic acid that's naturally in our system. When we do that, okay, breathe heavily, then our blood pH goes high, our amount of acid in our body becomes low. And so, what do you do for these folks who breathe too much? You give them a paper bag to breathe in. And the reason why you do that is you need to circulate the carbon dioxide back into the body. Okay. Metabolic alkalosis are people who like maybe throw up too much and they get rid of their natural hydrogen ion um, in their system. Um, these are the mechanisms by which they occur, but I really want to show you this. This is the buffer. Whenever you have a buffer, any excess hydronium ion will get chewed up and form its conjugate base. That's the key to removing hydronium ion. In the buffer, the back reaction also works because any excess hydroxide ion will react with that acid to form water and form the conjugate of that acid. So the key here is that the buffer physically removes the hydronium or the hydroxide. And without excess hydronium or hydroxide, the pH doesn't change. That's a buffer. Okay. So take a look at that. And next time we'll look at titration and finish off this chapter. And then probably when we finish off this chapter, I'll introduce a little bit of thermodynamics because we should be covering thermodynamics. But um, the next section, titration of weak acids and weak base, is basically the accumulation of what we already learned in the buffer section and in the acid base section. So if you have that knowledge, we're just putting it all together in one problem. That's the titration curves.